Right. Well, thank you for the invitation and for putting this wonderful program together. Too bad I can't be there in person. David has beach, we have mountains, and sometime while walking in the mountains, we think about sort of fundamental questions in statistical physics, and that's what I'll be telling you about today. So, before I begin, maybe let me thank various people that have been involved along the way. I think special thanks go to four people, my collaborator Vedika Kemani from Stanford, Boulder postdocs David Stephen and Oliver Hart, and my student Charlie Stahl, plus various others listed at the bottom. Okay, so maybe to motivate today's talk, let me start by saying that look, non-equilibrium systems are here there be dragons territory. When you're non-equilibrium, you can have entirely new sorts of phases of matter and new sorts of phenomena with no equilibrium analog. Yeah, and that's what this whole conference is about, after all. And one way in which we can be non-equilibrium is to break ergodicity. So, fundamental idea of the ergodic hypothesis that the system can explore all of its microstates, and if that's not true, then the second law of thermodynamics doesn't apply, and standard statistical physics doesn't apply. Yeah. And how can we break ergodicity in many-body quantum systems? Well, the oldest answer, of course, is integrability. And as a variation on that, these days there's quantum scars. But both of those are fine-tuned phenomena in the sense that there's a particular point in the space of all Hamiltonians where you have integrability and or quantum scars, and you perturb away from that point even a little bit in the thermodynamic limit, it's entirely possible that ergodicity is restored on a timescale that's only, let's say, a low-order polynomial in the perturbation strength. So I want something a bit more robust than that. And is there a way to break ergodicity in a manner that's more robust than either integrability or scarring? And the answer is yes. And this talk, I'll sort of talk about three different ways to do it, which are sort of increasing robustness in a certain sense. And that'll be many-body localization, fractonic symmetries, and emergent higher form symmetries. So let's start with many-body localization. I won't spend very much time on this because you've already had pedagogical lectures on the topic from David Hughes and John Imbrie, but I would be remiss if I did not even mention it. So the idea behind many-body localization is this is something that happens in systems with strong quench disorder, perfect isolation, and energy conservation, at least in the flow K sense, and it's robust in the following sense. There exist exactly solvable points where the localization is exact, and when you perturb about those exactly solvable points, the time scale on which ergodicity is restored is generically super polynomially long in the perturbation strength. Yeah, for the special case of 1D spin chains, it might even be infinite, modulo the fact that the spin chain model itself will not be a good description to infinite times, but the generic behavior, if you're in higher dimensions, long-range interactions, whatever, is that the timescale will be super polynomially long, longer than any polynomial function of the perturbation strength as you take perturbation strength to zero. And this is the sense in which it's more robust than, say, integrability, where timescales could be just polynomial. Okay, that's all I wanted to say about many-body localization. You've already had pedagogical lectures on the topic, so I won't keep banging on about it. Instead, now let me talk about a different route to ergodicity breaking, which involves what I'll call fractonic symmetries. And this was really inspired by the study of fracton phases of matter, which are a sort of exotic quantum phase of matter. You could think of them as generalized spin liquids. You don't need to know about fractons for the purposes of this talk. What you do need to know is that this is an alternative route to ergodicity breaking, which, unlike MBL, it does not require energy conservation, but instead it requires the imposition of a finite number of conservation laws, and a minimal sufficient set is to demand conservation of charge and also dipole moment of charge. Yeah, and why these two conservation laws? Well, that's sort of inspired by the study of fractons. This is also going to require strict locality, so for the purposes of this part of my talk, I will be assuming that my dynamics is generated by operators which have compact support, so not even exponential tails. Okay, so everything should be made as simple as possible and no simpler. The simplest possible setting in which we can realize this physics is a 1D spin chain. I should emphasize the physics is not limited to one dimension. You can get it in higher dimensions also, but let's start by thinking about one dimension. So we'll consider a 1D spin chain, and it's convenient to consider spin 1. And by charge, I mean the by charge, I mean the z component of the spin, and by dipole, I mean the position-weighted z component of the spin. And those are two quantities which we want to be conserved by the dynamics of this model. And what that straight away tells us is that a single charge is immobile, because if a charge hops either right or left, that changes the dipole moment of the problem, and dipole moment must be conserved. However, if we have a pair of charges, plus and minus, next to each other, which we could call a dipole, this object is freely mobile. And you can also have processes like this, which you could interpret either as charge hops to the left and emits plus minus dipole to the right, or as charge hops to the right and emits minus plus dipole to the left. Yeah? Okay, so we wish to consider the most general quantum dynamics, which respects these two conservation laws and is locally generated. So, the simplest way to implement that is in a quantum circuit model. Yeah. So here, you have some quantum state. The dynamics is generated by acting with various layers of these quantum gates. Each of these quantum gates is a little unitary. If you're not used to thinking about circuit dynamics, you could think of this as a sort of Suzuki-Trotter decomposition of Hamiltonian dynamics. Yeah. But the nice thing about circuit dynamics is that it has spatial locality built in from the get-go. Each of these gates has compact support, and you can further demand the charge and dipole conservation by demanding that each of these unitaries respects charge and dipole symmetry. But other than that, we place no further constraints on the problem. Now, within each charge and symmetry sector, this is just random matrix. So these gates, they could be chosen uniformly in space or randomly in space. They could be chosen uniformly in time or randomly in time. Of course, if they're chosen randomly in time, there's not even energy conservation. It turns out the physics is insensitive to whether we have translation invariance in space or not, whether we have translation invariance in time or not. Yeah? Okay, so what do we get? Well, what should we expect? Well, the model is so minimally structured, it doesn't even have energy conservation. The naive guess would be that we should have ergodicity. And what does ergodicity mean? Well, ergodicity would mean you start in a system with a particular value of charge and dipole moment, and then the system explores all of its microstates with the same value of charge and dipole moment. Yeah? So what these plots on the left show is what you would get in an equal weight superposition over all microstates with a given charge and dipole moment. That's what you would get for a long time average of the charge distribution if the system was ergodic. And you can see that if the system was ergodic, then charge would spread essentially uniformly across the system. And what's shown on the right-hand side is what you actually get if you, let's say, start the system off with charge sitting on site number 4 and then run the dynamics numerically. And you can see that what you get on the right looks very different from what you would expect based on ergodicity. What you see looks an awful lot more like localization. Okay? So this is something we first saw numerically, originally didn't understand. Empirically, numerically, for 3-side gates, charges are localized for almost any initial condition. If we generalize to longer range gates, then typical initial conditions appear to thermalize, but there is still an exponentially large subspace which does not. And this cannot be conventional localization, either Anderson or MBL, because there's no energy conservation, and there also need not be any disorder in the problem. So what is it? This explanation came in these two papers, which appeared on arXiv the same day. I'll give you the version of the explanation, which is from our paper, which I guess I like, although I'm obviously biased. So it's nice to understand things pictorially. Let's view things pictorially in the following way. So we have a spin 1 chain. Let's call plus the state of maximally positive charge, SZ is plus S, minus the state of maximally negative charge, SZ is minus S, and let's consider a state which alternates between all plus and all minus regions. So all plus and all minus regions are separated by domain walls, and let's consider a state where the domain walls are at least as far apart as the biggest operator which generates my dynamics. Now, let's consider the subsequent dynamics of this state. So I come in and I act with my gates. Each gate acts across either 0 or 1 domain walls, never across two domain walls because the domain walls are too far apart by construction. If it acts across zero domain walls, it acts on a region that's locally extremal charge. Nothing you can do to that consistent with charge conservation. If it acts across one domain wall, it acts on a region that's locally extremal dipole. So if you shuffle the charges around, that changes the dipole moment. Again, there's nothing this gate can do consistent with dipole conservation. Yeah. So any state of this form must be an exact eigenstate of any dynamics which conserves charge, conserves dipole, and is locally generated on the scale M. Now, how many states like this are there? Well, you can take your system, you can carve it up into blocks of size M. Each such block you can allow to be either all plus or all minus. So that gives you a number of states that's exponential in system size. This is just a lower bound. It's not tight, but it's sufficient to make the point that there are exponentially many in system size product states, which are exact eigenstates of any quantum dynamics with two conservation laws and spatial locality on the scale M. I should say all of this generalizes to higher dimensions. Generalizes by induction. So you could start off by doing stripes, and stripes would give you, a number of states which is exponential in linear system size. Now, if you have a two-dimensional system and you conserve dipole in both the x and the y directions, then you can actually allow the stripes to roughen a little bit and make the argument I just made first in the x direction and then in the y direction. That'll give you x plus L squared localized product states. And the process continues by induction to any number of dimensions. If you're in d dimensions, conserving charge in all components of dipole moment, then you have a number of localized product states, which is exponential in system volume. Yeah, works in any number of dimensions. Just every time you go up in dimension by one, you add one further conserved component of dipole moment. Unlike MBL, there's no subtleties about resonances. This is just sort of completely clean analytical of closed form argument. Okay, now let's zoom out a little bit more, talk about the time evolution. Time evolution is always generated by a unitary matrix. Quantum mechanical time evolution is unitary. This unitary matrix is always block diagonal by symmetry sectors. So quantum dynamics cannot change the symmetry quantum numbers of the problem. And in ergodic systems, that's it. Each symmetry block is a random matrix. What do we have here? Well, what we have here is that, as always, the unitary matrix is block diagonal by symmetry sector. But further within each symmetry sector, it further block diagonalizes into exponentially many Krylov subsectors with a very broad distribution of block sizes. So there's these 1-by-1 blocks, which are these exact frozen eigenstates that I was just talking about. But then there's blocks with size 2-by-2, 10-by-10, 50-by-50, and so on. Yeah. And the dynamics cannot connect states in different Krylov subsectors, even if they have the same symmetry quantum numbers, and that just follows from two conservation laws plus spatial locality. So this is the phenomenon that's called Hilbert space shattering or Hilbert space fragmentation, and it's robust to any perturbation that respects the two symmetries and strict locality. So the dynamics has to be generated by operators with compact support. These conservation laws may seem somewhat baroque. Now, how do you get conservation of dipole moment? In fact, there's very simple ways to do it. Maybe the simplest way is to consider ultra-cold atoms in a tilted potential. So if you have a tilted potential, then the potential tilt coupled to center of mass. Center of mass is the analog of dipole. Mass is the analog of charge. And so if you have an energy conserving system in a tilted potential, then you naturally get center of mass conservation, which is analogous to dipole moment conservation. And this is the manner in which this sort of phenomenon of Hilbert space shattering fragmentation has in fact already been observed in experiments. There are also other sort of like more complicated implementations. Okay, so what have we accomplished thus far? We found an alternative route to ergodicity breaking, entirely different from MBL, which proceeds through this Hilbert space shattering, Hilbert space fragmentation phenomenon, has nothing to do with disorder, has nothing to do with energy conservation. Instead, it relies on two symmetries and strict locality. And as long as you have two symmetries and strict locality, you're golden. Now, it's still somewhat limited. You can perturb with anything, but the thing with which you perturb has to be strictly local geometrically, and it has to respect these two symmetries. Can we get ergodicity breaking that's robust to arbitrary perturbations? Now, can we get ergodicity breaking that's even robust to non-local perturbations? This seems like a very, big ask. You don't get that with MBL. No, you don't get that with these charge and dipole models. But in fact, it turns out there is a way to do it, and the way to do it is to leverage higher form symmetries, and that's what the rest of my talk will be about. So now let's talk about topologically robust ergodicity breaking from emergent higher form symmetries. So what are higher form symmetries? Well, you have global symmetries where the symmetry operators live in the whole of space. You have gate symmetries where the symmetry operators live on points. Higher form symmetries are intermediate between the two. The symmetry operators live on manifolds with dimensionality bigger than 0, but less than the dimensionality of space. And they have the property that the charges of higher form symmetries are extended objects. Yeah? And it turns out that emergent higher form symmetries can give rise to robust and analytically provable ergodicity breaking with topological stability. And in fact, it has very simple geometric proofs of stability. All we require to get this to work is we require enforcement of a single constraint. If the constraint is enforced exactly, then our results will be exact to all times. If the constraint is enforced softly, i.e. energetically, then the results will be valid out to times that are exponentially long in perturbation strength, or exponentially long in the gap that's enforcing the constraint. Again, it's nice to illustrate things by explicit example. The simplest explicit example is what we call the CZP model. So let's work on the square lattice, spin 1/2 on the square lattice. For now, we can do periodic boundary conditions. That's not essential. The Hamiltonian takes the form H0 plus V, and I claim that V can be anything as long as it's k-local. So it could be sum over Pauli x's on every site. It could be sum over xi, xj, where I and j are chosen freely anywhere on the lattice. It could be sum over ijk, xi, yj, zk, where again, I, j, k are chosen freely on the lattice. They don't even have to be geometrically close to each other. The only requirement is that it's k-local, meaning that it's a sum of terms where each term acts on at most k degrees of freedom, and k is a vanishing fraction of system size in the thermodynamic limit. And I claim that this system will exhibit ergodicity breaking for any k-local perturbation V. Yeah? So obviously the magic is in H0. What's H0? Well, H0 has the following form. It's sum of all plaquettes, control Z plaquette. So control Z plaquette you could think of either as product of control Z gates around the 4 links of a plaquette, or you can make it out of Pauli Z operators in the manner shown down here. So it's it's ZZ operators on the diagonal and ZZZZ operators around each elementary plaquette. Yeah. And essentially what this operator does is it gives a large energy cost to having an odd number of neighboring upspins around any elementary plaquette. Yeah. So you can think of this Hamiltonian H0 as essentially enforcing a constraint. You want to work in the subspace which has eigenvalue +1 for each of these control Z plaquette operators. How big is this constraint subspace? Well, actually, you can do an exact count, and it's this big. It's about 1.5 to the power L squared, which means that this constraint subspace is exponentially large in system volume. So it's large enough to accommodate a non-zero entropy density, and it's sensible to talk about thermalization or lack thereof in the subspace. Now, to understand the physics of the problem, it's actually nice to invoke a duality. So this model is defined on the square lattice. The square lattice is bipartite, and it actually has 2 Ising symmetries. So if you do global Ising spin flip on either the odd or the even sublattice, then the Hamiltonian H0 is unchanged. So it's natural to go to the domain wall representation of the Ising model. So we have 2 species of domain walls, red and blue, which correspond to the domain walls of the Ising symmetry on the odd and even sublattice respectively. And the constraint that control Z plaquette has to be +1 amounts to saying that the red and blue domain walls cannot intersect. So the low energy, the constraint satisfying Hilbert space is a Hilbert space of closed loops in two colors, red and blue. They're closed loops because domain walls never end. And these red and blue loops cannot intersect. Anytime the red and blue loops intersect, as they do on the right, this costs a very large energy. Yeah, so it's sort of off in some high energy manifold. What do perturbations do? Perturbations lead to fluctuations of these loops subject to the constraint that red and blue loops cannot intersect. Okay? So now let's consider a state of the following sort. This state is a dense packing of system spanning loops in alternating color, red, blue, red, blue, red, blue. These loops can wiggle any which way, but they need to wiggle uniformly. So there's an exponentially large number of these densely packed configurations. The number of these densely packed configurations is exponential in linear system size. But once you've made these one of these densely packed configurations, there's no subsequent possible dynamics for these loops, because any local fluctuation is going to lead to crossings, which is going to take you out of the constraint manifold. And in fact, the only way to get back inside the constraint manifold is essentially to push one loop through the other, which involves acting on order L spins at once. And we cannot do this at any finite order in perturbation theory using a k-local perturbation. So these densely packed configurations are frozen to all finite orders in perturbation theory with any k-local perturbation. And now if the constraint that you can't have these intersections, if the constraint is imposed as a hard constraint, then the stability of these states is absolute. They'll live forever. If the constraint is imposed as a soft constraint, meaning you can violate it, but it just costs some large energy, then you can lean on the standard rigorous theory of prethermalization to show that these states are robust at least up to a time scale which is exponentially long in the constraint gap divided by perturbation strength. Okay, I want to be a little bit more, sort of dig deeper on this problem. So this problem actually has an emergent U1 one-form symmetry. Anytime you have a symmetry, you should resolve by the symmetry. And one-form symmetry means the symmetry charges are loops. So what we would naively expect if we had ergodicity is that the approach to equilibrium would be fluctuations of loops. So that's magnetohydrodynamics. So we can compare to magnetohydrodynamics, and what we see is the following. We have a big unitary time evolution matrix. It block diagonalizes according to symmetry sectors of this emergent one-form symmetry. And then there's two sorts of symmetry sectors. There's one sort of symmetry sector in which the dynamics is ergodic, and it follows magnetohydrodynamics. So hydrodynamics of fluctuating loops. And there's another sort of symmetry sector which is made of these densely packed configurations, which is completely frozen. There's no dynamics whatsoever. So we conclude that within this CZP model, there is ergodicity breaking, but it's all or nothing in character. There's some symmetry sectors which are ergodic, and there's other symmetry sectors which are completely frozen and have no dynamics whatsoever. Now, this all or nothing character of the ergodicity breaking is actually particular to this specific model, the CZP model. So we can actually generalize in a way that the ergodicity breaking is not all or nothing anymore. So one way in which to generalize it is to go from spin 1/2 to M state clock spins. So we can write down a series of models on, let's say, square and cubic lattices, which are labeled by two integers. There's the integer M, which is how many states the clock spins have, and there's the spatial dimensionality D. And if M is 2 and D is 2, then you get back the model I was just telling you about. But if you make M and D bigger than 2, M or D bigger than 2, then you get richer behavior. And in particular, you become able both to extend the results to open boundaries, and also the ergodicity breaking is no longer all or nothing. So now let me sort of show you how that works. So the simplest extension is to make M3. So we have 3 state clock spins on the square lattice. So now we have 3 species of domain walls, red, green, blue. As before, the domain walls of different colors cannot intersect. As before, the constraint satisfying Hilbert space is exponentially large in system volume, so it's big enough to accommodate a non-zero entropy density, so we can meaningfully talk about thermalization or not. The low energy Hilbert space is the Hilbert space of now 3 species of loops, where loops of different colors cannot intersect, but they can fluctuate in any which way. And now let me consider a state of the form that's shown here. Yeah, so this is not a dense packing configuration, but what we can do is we can walk from left to right across the system. And as we walk from left to right across the system, every time we encounter a non-contractible loop, we'll record the color of the non-contractible loop. Yeah. So for this pattern, as I walk from left to right, I would record green, red. And this sequence, green, red, this is a topological invariant of the dynamics. Yeah. Because there's no way to change it without pushing the red non-contractible loop through the green non-contractible loop. And that requires acting on order L degrees of freedom at once. And you can't do that with any k-local perturbation at any finite order in perturbation theory. And you can show that you can write down sort of finite thickness motifs, which are charge neutral, but have a non-trivial topological invariant associated to them. Yeah. So we see straight away that my quantum dynamics must not only be block diagonal by symmetry sector, it must further be block diagonal by topological invariant. We call this topological invariant the irreducible label, and this irreducible label is topologically robust. It cannot be changed at any finite order in perturbation theory by any k-local perturbation. Yeah? So simple counting tells you that there's polynomially many symmetry sectors, emergent symmetry sectors, but there's exponentially many irreducible labels. So ergodicity is broken with topological robustness, and now ergodicity breaking is there in generic symmetry sectors. Yeah. So there's still the densely packed sectors, but there's no dynamics whatsoever. But you look in generic symmetry sectors, and you have sort of standard Hilbert space shattering fragmentation picture, where you have Krylov subblocks with a broad distribution of sizes, and the quantum dynamics is not able to connect states in one Krylov subsector to states in a different Krylov subsector, even if they have the same symmetry quantum numbers. Constructions work just fine with open boundary conditions. They also work just fine, and they can generalize perfectly fine to higher dimensions. If you go to 3 dimensions, you want to use membrane models, and then you have a 2-form emergent symmetry, so on. Okay, so that brings me to pretty much the end of my talk. I'll just summarize. Textbook statistical mechanics relies on ergodicity. Ergodic hypothesis goes back to Boltzmann, assumes the system can explore all of its microstates. If the ergodic hypothesis is violated, then we're in here, there be Dragon's territory. How can we break ergodicity in many-body quantum dynamics? Well, we want to ideally break it robustly. So historically, the first example was many-body localization. Needs energy conservation, needs strong disorder, needs perfect isolation, robust to local perturbations. Then there was fractonic symmetries that requires 2 symmetries and strict locality, does not require energy conservation. Yeah. And most recently, we've discovered these sort of topological fragmentation route to ergodicity breaking based on higher form symmetries, emergent higher form symmetries. Now all we need is enforcement of a single constraint, and then we're robust to arbitrary k-local perturbations. Yeah. So this is I think the most robust form of ergodicity breaking that I know of in quantum dynamics. Now, is it possible to do better still? That would essentially be, is it possible to get it sort of to infinite times instead of just exponential times? I guess that's something we're still working on, but we don't definitely know of a way to do that yet. And with that, I will conclude, and I'm open to questions.
Questions, yeah.
Thanks for a very nice talk. I was just trying to flesh out this last slide you have here on conclusions. Because I thought, well, there's the question I have is with respect to which things can you allow in many-body localization, and I understand you have, even with flow K driving, you still believe that there's many-body localization, so that it shouldn't necessarily require energy conservation.
Well, it at least needs Floquet energy conservation.
Okay,
So
all right.
no,
And then another thing you made during the talk, a statement you made was you needed locality.
right.
In what sense
So
locality? I mean, I
for
would
many body
presume.
localization, I guess we can tolerate exponential tails.
Oh, okay. So,
Right.
okay. So you weren't talking
For the
about.
fractonic symmetries route, we cannot even tolerate exponential tails. We really need compact support.
Okay.
But this higher form symmetry stuff, you know, you can have power law tails, you can have like infinite range interactions. It's all fine.
Okay. Thanks.
So for dipole conservation,
Yeah.
is there some simple way to enforce it using, say, two-side unitaries, perhaps in some effective
Right.
way?
So if you limit yourself to two-site unitaries, then the problem is manifestly trivial. You cannot write down any non-trivial dynamics which conserves charge and dipole and acts with only two-site unitaries.
Yeah.
So then your Hamiltonian is identity.
Yes.
So the 3 sites is the minimum that you need to get like, non-trivial dynamics with the dipole problem.
And to perhaps get it in some emergent, effective way, like.
Yeah, the simplest way to get the dipole problem in an emergent effective way is to consider cold atoms in a linear potential.
Okay.
Right. So atom number is charge and center of mass is dipole, and the potential tilt couples to center of mass. So if the tilt is strong, then center of mass will be conserved in a pre-thermal sense. So that's pre-thermal conservation of dipole moment.
Okay.
Actually, could I ask another question about this slide?
Sure.
What's the second panel there that looks like a sort of quasi-crystal construction?
Yeah. So panel A is in 1 dimension, right? You could wonder if you could do this in dimensions bigger than 1. So something that you could imagine doing, I don't think anybody has done this in experiment yet, but you could certainly imagine doing it, is have some 2D square lattice and then put your potential tilt at an irrational angle to the lattice axis. So if it's at an irrational angle, then in the direction of the tilt, you have this dipole conserving problem, which localizes, but not for reasons of disorder, for reasons of Hilbert space shattering. And in the transverse direction, you have what effectively looks like quasi-periodic disorder. Yeah. So now you would have sort of like dipole localization in one direction and quasi-periodic localization in the transverse direction.
That's super cool. Thanks.
So I had a follow-up on John's question.
Right.
Why do you say that you even need, I guess, a quasi-energy conservation for MBL?
Right. So the basic mechanism for MBL is that perturbations take you off energy shell, essentially, right? So if you construct a locator expansion a la Anderson, then the way it works is you have matrix elements and you have energy denominators, and you want the matrix elements to be small compared to energy denominators, at least typically. I mean, when they're not, that's a resonance, and you need to show that the resonances don't percolate. But if you don't have energy conservation in the first place, then like, what are you talking about?
Well, but
so that's maybe an intuitive way to answer it. A crisper way to answer this is, look, if you have an MBL system and you place it in contact with a heat bath, so that like you're not microcanonical anymore, you switch to the canonical ensemble and you're allowed to borrow energy from the heat bath, then in fact the system will thermalize, and it will thermalize on timescales which will be power law in the coupling to the heat bath. Yeah. And if the heat bath is featureless, then it's just the Fermi's golden rule timescale. If the heat bath is crippled in some way, like maybe it's very narrow bandwidth or something, then you can get higher powers, but it's still fundamentally power law. So like Sarangopalakrishnan and I had some series of papers on this a decade ago. But yeah, you really need energy conservation. So like
but quasi-energy conservation is okay?
What? Yeah, Floquet energy conservation is maybe good enough.
All right.
Yeah.
So
I mean,
agree,
people
like,
sometimes say that localization is an interference phenomenon. I think this is only really true for Anderson localization, not for MVL. I mean, Anderson localization has this nice weak localization picture. Like there's nothing like a weak localization picture for MVL. The only sense in which we really understand it is something more like strong localization, which is like based on a locator expansion type picture where you need matrix elements small compared to energy denominators.
Right, I agree with that. And for sure, like if you have an open system, MBL should destabilize. But just flow K is probably too restrictive. Like you can have like at least based on like the perturbative like expansion that you were talking about, it's okay to have quasi-periodic driving, right? And then you can still have those matrix elements like decay faster than the energy denominators.
I mean, I confess I'm actually a little skeptical of both Floquet and of bang-bang Floquet protocols and, bang-bang quasi-periodic protocols.
Yeah, for sure. Yeah, it's smooth in both cases.
Yes. If you do sinusoidal two-tone driving, you can probably get away with that. Yes.
Thanks for the nice talk. I have a general question about these constraints. So if you impose a constraint on some local degree of freedom or local degrees of freedom, is it necessary that it is associated with a symmetry, or can it be just anything else? And then you probably wouldn't have like a gauge theory.
So I think you could always view it as a symmetry in the following sense. Let's say we impose a constraint, and constraint violations cost some energy. So now you can sort the Hamiltonian into manifolds, which are labeled by the number of constraint violations. And now you could introduce a symmetry where the symmetry charges are the constraint violations. And then now the different manifolds are just labeled by symmetry quantum number, which is number of constraint violations.
And would that be a gauge symmetry or not?
I mean, so for the example of for this constraint, this CZ plaquette constraint, it turns out to be a one-form symmetry. So it's not a global symmetry, it's not a gauge symmetry, it's something in between.
Okay, thank you.
Okay, if not, let's thank Rahul again.